Okay, thank you, Paul, and thanks for the invitation from CMIP Seminar. My name is Song Zongpeng, presenting on behalf of our research team. Today's talk is titled Projecting the Evolutionary Path of China's Photovoltaic Potential Using CMIP Climate Models, published this year in Sustainable Energy Technologies and Assessments. Let's get started. My presentation covers several sections. We will move through background, data and methods, model selection, projections, turning point analysis, driver decompositions, and finally policy implications. The scientific core is sections 3 through 6. I will spend most of our time there. China leads the world in solar power installations. By end of 2025, installed PV capacity reached 1.2 terawatts, 43% of global total. Solar is no longer supplementary. It is central to China's carbon neutrality pathway. Yet a fundamental question has not been clearly answered. As the climate changes over the rest of this century, how will China's PV resource, not just installed capacity, actually evolve? The literature is generally divided. Some studies project growth under high emission scenario, others project decline. This contradiction is not just academic, it sends conflicting signals to energy planners and investors. The root problem is insufficient scrutiny of which climate models are actually accurate, and the lack of a rigorous decomposition of the competing physical mechanism involved. Our study addresses both directly. Our study integrates three data streams. First, 15 CMIP6 models data are collected, including three emission scenarios, providing irradiance, temperature, wind, cloud cover, and aerosol optical depths. Second, high precision observational graded data sets are collected. Third, ERA-fine hourly reanalysis data is used to reconstruct the typical daily variation pattern for each calendar month. The last step is critical. CMIP outputs are monthly averages, but PV port output depends on subdaily solar intensity variations. ERA-5 bridges that gap. The method has 4 components shown here alongside the there are little problem, but it's okay. The PV potential index quantifies the fraction of rated output achievable under real-world conditions, accounting for irradiance, temperature, and wind speed. Module efficiency degrades at 0.4% per degree Celsius above 25 degrees Celsius. This temperature sensitivity is the physical foundation of the warning effect we will discuss later. For model evaluation, we apply linear regression to the history period, focusing specifically on the rate of change and its statistical significance, not a mean bias. We care about the long-term trend, not short-term fit. Low-pass filtering then smoothes the project series to remove interannual noise, enabling clean identification of trend reversals through first and second derivatives. Finally, driver decomposition uses motivated regression to attribute year-by-year PV port changes to temperature, irradiance, cloud, and aerosol. We evaluate all 15 models against observational. For temperature, the result is clean. 14 of 15 models correctly reproduce the trend and reproduce the significant. No surprise there. The critical discriminator is irradiance. The observed irradiance shows a decline trend, but this trend is not statistically significant. More importantly, the rate of decline slowed noticeably after the 1990s as China's aerosol emissions began to stable. This is a subtle but physically meaningful feature. Only 4 models correctly reproduce this. The two exercise model from Australia, IPSL CM6A LR model from France, and the KIOST ESM model from Korea. They match both the non-significance and the post-1990s deceleration. This is the high accuracy ensemble that is MM4. The remaining 11 MM11 overestimates the significance of irradiance decline, indicating systematic biases in aerosol cloud radiation interactions. Using MM4 ensemble, we obtain 3 distinct evolutionary pathways, shown both as scenario curves on the left and as the actual time series on the right. Under SSP126, PV port grows throughout the century. A turning point in 2034 marks the shift from rapid early growth to a sustained long-term increase. This is the most favorable scenario. Under SSP245, PV port initially declines, then recovers. Okay, under SSP585, PV port rises until 2035, then declines for approximately 60 years until 2094, directly encompassing China's 2060 carbon neutrality target. This is the critical risk scenario. This slide compares. This comparison table makes the stakes of model selection concentrate. For SSP126, both ensembles agree. For SSP245, there is a minor quantitative difference. The critical case is SSP585. MM4 projects a clear multi-dimensional decadal decline after 2035. MM11 shows essentially no significant trend, nearly flat. This is not a quantitative disagreement. It is a quantitative difference about whether a major long risk exists. The source traces back to M11's historical bias. It overestimates the irradiance decline trend before 2040, suggesting it either over-responds to aerosol brightening or underestimate warming-induced radiative suppression. This slide synthesizes the conceptual heart of the paper. The left panel shows the two competing forces. Brightening runs through a chain. AOD decreases, cloud cover weakens, irradiance rises, faster gains from 2010 to 2030, then diminishing returns. Warming runs a different chain. Temperature rises, water vapor and cloud liquid water path increases. Irradiance is surprised, and the module efficiency fall directly. Slow start, then nonlinear acceleration. The center panel answers the key question: why do turning points concentrate in this specific period? Three reasons. First, aerosol gains plateau. Once air quality reaches a cleaner baseline, marginal brightening returns diminishing sharply. Second, warming enters its nonlinear phase. Post-2030 temperature rise accelerates, amplifying radiative feedbacks. Third, the intersection is therefore structurally locked into this early century window. The right panel addresses the scenario asymmetry. SSP 85 tends later than SSP 2 because its stronger initial aerosol reduction delays the crossover. Despite its fast warming, early brightening wins in this model, but once the flip happens, the decline is far more severe. The core finding, this window marks the transition from a pollution-driven era, where air quality governance dominates PV resources, to a climate-driven era, where global warming becomes the decisive factor. Before the results, here is a three-step framework we use in driver decomposition method. Step 1. Fit two regression models on the full 2050 to 2100 filtered series. One predicting pure port from T and I, one predicting I from cloud aerosol and T. Step 2. For each year, compute year-over-year contributions at two levels. At the PV port level, changes decompose into a direct temperature term and a direct irradiance term. At the irradiance level, the change itself further decomposes into cloud, aerosol, and temperature-related radiative components. The irradiance result feedback into PV port irradiance term, creating the two-layer hierarchy. Step 3. Integrating across all years give full hierarchical attribution, revealing not just what changed each year, but why at every point in the project pathway. Now the results across all three scenarios. Okay, one by one. Under SSP 126, the picture is clean. Panel B shows the PV port change dominated entirely by the positive irradiance contribution. Temperature's role is negligible throughout. Panel C confirms that this irradiance gain is driven primarily by aerosol reduction, with cloud cover showing no meaningful trend. The brightening effect runs essentially uncontested. Under SSP2, the mechanism is more complex. Before 2028, both contributions are suppressed. After 2028, irradiance contribution flips strongly positive, not driven by both aerosol and cloud reductions. Unlike SSP1, which relies on aerosols alone, the temperature effect is also more pronounced, meaning the post-2028 recovery requires both environmental levels working together. Under SSP 585, the decomposition tells the definitive story. After 2035, the temperature contribution escalates dramatically and turns dominant. Simultaneously, the irradiance contribution itself weakens because warming is not suppressing the solar resource through water vapor absorption and increase cloud optical depth. This is the dual constraint. Temperature simultaneously degrades what module can do with available sunlight and reduces how much sunlight is available at all. About the physical mechanism, why SSP 585 decline is so severe and sustained. Constraint 1 is direct. By 2100, warming over 6 to 8 degrees Celsius causes substantial performance ratio losses. No constraint 2 improvement can compensate this temperature level. Constraint 2 is indirect. Warming increases atmospheric moisture following the Clausius-Clapeyron relation, strengthening shortwave absorption and reducing surface radiation. Simultaneously, higher temperature increases cloud liquid water path, making clouds optically thicker and more reflective. Both pathways act in the same direction, reinforcing each other. This is why it shows a sustained decline from 2035 all the way to 2094. About the policy implications, our findings support three clearly different strategies, one per scenario. Under low emission, expand aggressively. Resources are reliable and growing. Aerosol reduction through continued environmental policy is the primary lever. Long-term investment returns are stable. Under medium emissions, plan adaptively. Anticipate volatility around the 2028 turning point during the 15th five-year plan. Focus on efficiency R&D before 2030, then scale up capacity as growth resumes. Co-manage both aerosol and cloud-related places. Under high emissions, pivot to risk management. Prioritize resistant PV technology R&D advance energy storage, and diversify the energy portfolio. The 2035 to 2060 interval is critical. It is precisely when PV port is declining, when carbon neutrality targets demand peak solar performance. Investment in adaptive infrastructure must begin now. The unifying message at the bottom, scenario appropriate planning grounded in MM4 quality projections is a prerequisite for energy security, not an academic exercise. To close, the feature of solar PV in China is not a straight line. It is a complex interaction of physics, aerosols, and temperature, and which path we follow depends entirely on emission choices. Under low emissions, aggressive expansion is justified. Under high emissions, the strategy must shift fundamentally to resilience, storage, and adaptation. The move from one-size-fits-all planning to scenario-dependent strategy backed up by physically rigorous model selection is the central message of this work. Okay, thank you for your attention.
Thank you, Zongpeng. That was very interesting. Unfortunately, we've run out of time. I did have a very, very quick question. Do you think that the use of perovskite cells could offset the reduction in efficiency for the solar panels? Is there any, there is research going on in the use of perovskites because they're more efficient. So maybe that could offset the warming if under a higher scenario. But I wondered whether there was...
the PV technology developed very fast. I think the efficiency is growing. Yeah, and Elon Musk want to send the PV panel PV cells to the space. Yeah, I think the future will change.